Hi everyone, welcome to the fourth lesson for topic 3.3 Graphs and Networks. So for today's lesson, we are still under the subtopic of paths and cycle, but we are looking at two different learning outcomes. So it's a bit long here, so I'm not going to go through everything, but I just want you to remember that after today's lesson, you should be able to understand the meaning of the terms of what is that meant by Eulerian graph and semi-Eulerian graph. That's the first thing. Second thing, what is that meant by Hamiltonian graph and semi-Hamiltonian graph? Okay, so after you understand the definition of each of these terms, then you should be able to use it or you should be able to apply them according to the context of the question. All right, so for today's lesson, we are going to look at it with like four different parts. So the first one will start with some recap of the prior knowledge that you need to know. So for example, the degree of the vertex that we have discussed previously, and also the type of works in lesson 3, and also what is that meant by transversability. Okay, then after that, we'll be looking at an overview of this lesson. So we are going to look at these two learning outcomes in one table. So after we look at the overview, right, it's like the summary of the type of works that we have previously. So the overview of this lesson. Then after that, we'll be looking at the first part, which we talk about the Eulerian or semi-Eulerian. Then after that, the second part, we are going to talk about the Hamiltonian graph and semi-Hamiltonian graph. Okay, so that's basically the plan for today's lesson. So let's start with the first part, which we discuss some of the prior knowledge that you should know before we move on to the content of today's lesson. Alright, so there are three things that we are going to discuss here. So the first one is what we have mentioned in our first lesson when we first started this topic, which is called as the degree of vertex. Okay, so we know that the degree or the order of the vertex is the number of edges incident with the vertex with loops counted as twice. Okay, so I hope that you still remember how to calculate this, and I'm just going to add in some of the information that you'll be using later. Okay, so the first one, let's try to look at vertex A. Alright, so I hope that you still remember, so which means that you can find out how many edges incident with this vertex. So for example, for the vertex A here, so you have 1, 2, 3, and 4. So the degree of vertex A is just 4. Okay, so now let's look at B. So you have 1, 2, and then 3. So 3. So degree C here, so remember the loops counted as twice because you can actually move in then go back to C, or you can actually move out from this place and go back to C, right? So that's why 1, 2, 3, 4, and 5. So degree of vertex C is 5. Then for D, obviously 1, 2. Alright, so you can look at all the numbers that you have here. So the vertices of A and D is also known as even vertices because they are having a even degree. Okay, so you can see that 4 and 2 are even numbers. So that's why vertices A and D are known as even vertices or and vertices with an even degree. Okay, so for vertices B and C, they are having 3 and 5, right? The degree of 3 and the degree of 5. So these two vertices are known as the odd vertices because they are having a vertices with odd degree. Alright, so that's the idea. So remember how to differentiate this, and later when we are talking about Eulerian, then you should be able to know this. Alright, so the second thing that we are going to talk about here is called as traversability. Okay, a network is said to be traversable if it can be drawn without taking the pen off. So without taking the pen off the paper and without going over the same edges for twice. Okay, so the idea is you can pass through the same vertex more than once. Okay, so yeah, initially when this class supposed to be a face-to-face class, so yeah, I thought to actually just give you guys some time to actually explore about this game, which is called as a one-line drawing game. So you can actually help you to understand this idea of traversability better, but then now we can't do it, so you might search it yourself. Just do a very quick Google search, then you'll be able to get it. Okay, so but I'm just going to explain it in a very simple way. Okay, so for example, let me try to give you a picture here. Okay, so let's try to talk about this thing. Okay, so you have all right, something like this. Okay, so these are the vertices that you have. All right, so the task is try to think of, is there any way that you can go through all the edges in this diagram for once? Okay, so which means that you cannot go over the same edge, and then when you try to draw it, you cannot take your pen off. Okay, so which means that you should join every vertex here and you pass through all the edges here with only one line. Okay, so that's the idea. Okay, so you might want to pause the video, then you can spend like for 5 minutes to think about that, whether you can actually draw all the, connect all the edges here by using only one line. Okay, so yeah, I'm just going to show you very quickly here. Okay, so in this case, then you can try to think of, for example, what I can try to do is, yeah, I might want to go through here. So you can see I go through here, I go through here, go through here, go through here, go through here, go through here. So you can see I pass through all the edges here. I didn't repeat any edges, right? And I didn't take my pen off. So that's the idea of traversability. So which means that if I'm able to do that, then this network is said to be traversable. So which means that you can traverse through all the edges by using only one line. So remember that you can pass through the same vertex because, for example, when you look at, how I do it just now, right? So I actually pass through this vertex for twice or three or yeah for twice. So you can see that I go through here, I go through here and I come back to this vertex. Am I right? But I didn't repeat any edges. I only repeat the vertex here. Then I go through here, I go through here, then I go back. Okay, so this network here is actually a traversable network. All right, so that's the idea. Okay, so the last thing is the type of walks that we discussed previously in lesson 3. So please take out your previous handout because I didn't put in this handout because it's just like a lesson before, right? You can try to look at that, then we just try to do a very quick recap. Alright, I hope that you still remember this diagram. So in the previous lesson, we talked about type of walks, which we start with the definition of a walk. Okay, so we know that walk is just a series, a sequence of vertices such that you can travel from each of the vertices to another vertex by using only an edge. Okay, so which means when we talk about a walk of ABC, then which means A and B must be adjacent to each other and B and C must be adjacent to each other. So that's why they are directly connected to each other by using only one edge, then you can travel along the road. So this is called as a walk. Okay, so for a walk, right, you can allow repeated vertices and you can allow repeated edges. So I hope that from the explanation previously, you understand that this is not a must. So which means that walk is like a general definition. So you can allow these two things to happen, but it doesn't mean that it must contain of repeated vertices and repeated edges. As long as it's a road that you can travel by using only one edge, then it's called as a walk. Okay, then after that, we try to restrict this idea, right? Then so that we have the second term here, which we call it as a trail. Okay, so for a trail, you can allow repeated edges, but there is no repeated edges. Sorry, you can allow repeated vertices, but not repeated edges. Okay, so this is a must. So which means that a trail must not contain repeated edges. Alright, so as long as you have edges repeated, then it is not called as a trail anymore. Okay, then after that, we have the third one, which we call as a path. Then it's even more restricted, which it cannot allow both repeated vertices and also repeated edges. Alright, so that's the idea of it. So we also understand that a trail is a walk, a path is a trail as well, a path is called as a walk as well. So this is like a general idea, is a big umbrella. So under a walk, or we can try to look at it in a subset, you get what I mean, right? So which means in a big idea, we have walk. Then after that, trail is actually part of walk, which you didn't allow any repeated edges. Then a path is a part of a trail and also a walk, which you doesn't allow any of repeated vertices and repeated edges. And when we try to give a name to the walk, right, we always use the most accurate name that we can try to use. For example, if you can see that it's a path, then we will always use a path rather than a trail or a walk. All right, so that's the idea. Then the second thing we know about all this walk is the other way that we can try to look at it is that whether it starts and ends at the same vertex or not. So under walk, then we have open walk and we have closed walk. Okay, so which means that it's a road that you can start and end at different vertex is called as an open walk. Then if you start and end at the same vertex, then it's called as a closed walk. Okay, then for trail, then you also have a open trail and also closed trail. Depends on where you start and where you end, right? Okay, then after that, the last one for the path as well, you have open and then you have closed. So something special about the closed path is that because in path, we talk about you cannot have any repeated vertices, right? But for closed path, then which means that except the starting and the ending, you can actually repeat. Okay, because when we try to talk about a closed path, it should be start and end at the same vertex, right? If you cannot repeat any vertex, then which means you cannot start and end at the same vertex. So that's the only exception for path. So a closed path is also known as a cycle. Okay, so that these are all the content that we learned in a previous lesson. So for today's lesson, we are going to talk about something similar but in another context. So let's have a look at the content or the overview of today. So make sure that you are able to understand all these things before you move on. Alright, so let's start with the overview of today's lesson. Alright, the second part of the lesson, we are going to look at an overview of today's content. So hopefully you have this big picture in your mind so that you can understand better when we move on to every single detail later. Okay, so for today's lesson, we are going to look at some special cases when we travel within a connected graph. So if you can recall from our first lesson, connected graph is a graph that do not have any isolated vertex. So which means that every vertex in the graph, they should be able to connect it to every other vertex. Okay, so which means there's no disconnected vertices or edges in the graph itself. Okay, so there are two special kind of walks that we'll be looking at. Alright, the first case that we have here is we traverse every edges once. So remember, every edge. The second case that we have here is we traverse every vertex once. So every vertex. Okay, so now when we try to look at this thing, right? When we traverse every edges once, which means we do not repeat any edges. Am I right? And when we say that there's no repeated edges, what does that mean? It will actually give you a trail. If you can recall, am I right? So that's why the second case here, when we say that you visit every vertex once, then which means that you do not repeat any vertex. So a walk without any repeated vertex is called as a path. Okay, then you might have a question here. So if let's say we talk about a trail and a path, then what's the difference between today's lesson and previous lesson? So remember that for a trail and a path that we discussed in the previous lesson, right, which is like a general trail and path, you do not really need to include every edges. You get what I mean? So for example, okay, if let's say this is A, B, C, D, E, so in the previous lesson, when we talk about a trail, like ABC is a trail as well. ABDE is a trail as well, because you do not repeat any edges, right? But the trail that we are looking at today, right, is that you must go through every edges once. So it's a must for you to go through every edges. So that's why we will try to give it a special name, so which is called as a Eulerian trail. So this is the thing that we mentioned in the learning outcome for today's lesson. Okay, so a Eulerian trail is basically a trail where you passes through every edges once. Then for every vertex, so which means that when we talk about a path in the previous session, so A, B, C is a path as well because you do not repeat any vertex, am I right? But for today's lesson, we are trying to look at a path that we go through every vertex once. So which means you must pass through all A, B, like A, C, B, D, E. Okay, so this kind of path is called as a Hamiltonian path. Okay, so I hope that you can get this first idea, the difference between today's lesson and the previous lesson. So after that, it's the same thing. So under Eulerian trail, then we can actually categorize them into whether it's open or closed. So which means this trail, whether it starts and ends at different vertex or it starts and ends at the same vertex. So if let's say it starts and ends at different vertex, then it's called as an open Eulerian trail. So there's a special name given to it, which is known as semi-Eulerian. Okay, so semi-Eulerian trail. Or if we are referring to a graph that having a semi-Eulerian trail, you can call it as semi-Eulerian graph. Okay, so sorry, I think that you should actually write a little bit smaller. Yeah, because I try to like squeeze everything into like a page. Okay, then after that, for a closed Eulerian trail, so which means that you start and end at the same vertex, so it's called as a Eulerian circuit. So circuit is basically a closed trail, Eulerian circuit. Or if you are referring to a graph that having a closed Eulerian trail, then it's called as a Eulerian graph. Alright, okay, then for the second part, is the same thing here. So if let's say you have an open Hamiltonian path, then which means that it will be known as a semi-Hamiltonian path. So don't worry about all these names first. We are going to look at everything in a much more detailed way later, like one by one. Okay, so this is like to give you a brief idea on what you are going to learn later. So if for a graph that contain a semi-Hamiltonian path, then it's called as a semi-Hamiltonian graph. Okay, so we know that for a closed path, so a path which you start and end at the same vertex is known as a cycle, am I right? So that's why for a closed Hamiltonian path, it's called as a Hamiltonian cycle. Or if let's say we are referring to a graph that having this Hamiltonian cycle, then we call it as a Hamiltonian graph. Okay, so that's basically everything. So for the third part of the lesson, we are going to look at Eulerian trail. Then after that, we are going to look at Hamiltonian graph. Oh, sorry, Hamiltonian path. Alright, so let's start with the next part. Alright, let's try to look at the definition in a much more detailed and also written way. Okay, a connected graph is said to be Eulerian if it has a closed trail. Okay, so which means that it must start and end at the same vertex. Am I right? Closed trail, so close, so which means you start and end at the same vertex. And also when we talk about Eulerian, so which means that you must include every edges and once only. Okay, so this kind of trail is called as a Eulerian trail. So the second thing, a connected graph is semi-Eulerian if there is an open trail. Okay, so this is similar like what we discussed just now, but in a written way. So all Eulerian graph and semi-Eulerian graph are traversable. So remember what is that meant by traversable? So which means you are able to create or you are able to draw the graph by using one line without taking your pen off. And you only, go through all the edges once only. Okay, so for all the Eulerian graph and semi-Eulerian graph, you can repeat vertices. It's just that you can't repeat the edges. Okay, so later we are going to look at some of the example of Eulerian graph. Okay, so for Eulerian graph, right, there's something that there's some tips or there's some shortcut so that can help you to identify whether a graph is a Eulerian graph or not. Okay, so the first thing that we are going to look at is for Eulerian graph. So Eulerian graph, which means that you have a closed shell inside the graph. So for a Eulerian graph, all vertices of your graph must be of even degree. Okay, so in other words, you cannot have any odd degree vertices. So it must start and end at the same vertex. Okay, so how can you actually check that? So these are two of the example of a Eulerian graph. So which means that you can draw a Eulerian trail inside it. Okay, so let's try to check in terms of their degree first. So you can see that the degree of A is 2. Am I right? Then after that, the degree of B, what's the degree here? So you can see 1, 2, 3, 4. Okay, and the degree of C, you have 2. Okay, and degree of D, you have 2. And the degree of E, then you have 2 as well. So you'll realize here that you have 2, 4, 2, 2, 2. So which means that all the vertices here, they are in even degree. So you satisfy the first case. So now we need to identify a closed trail that starts and finishes at the same vertex and you are able to pass through all the edges. Okay, so for Eulerian graph, right, you can actually start anywhere as long as you can start and end at the same vertex and you pass through all the edges. Okay, so for example, if let's say I want to start from A, okay, so in this case, then I can pass through like A to D, then D to B, B to E, and then B to C, and then C to B, and then go back to A. So you'll realize that I actually go through all the edges only once without repeat any of them. Then I start and end at the same vertex. Okay, so in this case, let me try to write down my Eulerian trail. So which means it will be A, D, B, E, C, then B, A. So what can you realize here is that I actually go through or I actually repeat the vertex, okay? But then I didn't repeat the edges. So remember for Eulerian graph, so which means that you need to go through all the edges, but you can pass through the same vertices again. So the other words that you can try to describe it is that, yeah, for this network, it's a traversable one because you can actually draw this exact graph by using only one line without taking your pen off the paper, okay? And you do not repeat any of the edges. Alright, so if let's say you do not want to start with A, right, then you can always start with the other as well. So for example, if let's say you want to start with B, okay, then which means you also can do BA, then after that go to D, go to B. So even you want to go to C first, then go to E, and then go back to B also can. Alright, so in this case, then what is the trial that you have? Then it will be BA, D, then you go back to B, then you go to E first, you go to C, and then you go back to B. Okay, so which means BA, DB, or ECB. Alright, so this is a closed trail as well. So for in this case, right, you can have different answer in the form where you start at different vertex. But the idea is when you say that it's a Eulerian graph, you must start and end at the same vertex. Okay, so let's try to check out the other. Alright, so in this case, same thing. Let's start with the degree first. So the degree of, how come I didn't change the color? Okay, so the degree of V here, we have 1, 2, 3, and 4. So that's why degree of V is 4. Then the degree of W, so it's 1, 2, 3, 4 as well. So degree of X, so you can see 1, 2, 3, 4. So the same with Y and Z. Okay, so now you can see that every degree here is having like a degree of 4, so they are all even degree. So that's why this is a Eulerian graph. So now let's try to identify the trail that we can have. Okay, so if let's say I want to start with X here. Okay, so can I try to find out what's the road that I can pass through so that I go through all the edges once without repeat anything? So yeah, if let's say I want to go to Y first, so maybe I can go Y, V, I go back to Y, then go to Z, go to W, go to Z, go to X, go to W, go back to V, then go to Z. Okay, so as what I say, this is not the only answer. You can actually build your own trail as long as you start and finish at the same vertex and you pass it through all the edges. Okay, so in this case, then my answer here would be starting from X just now, right? So X, I also forgot already. X, Y, V, Y, Z, W, and then I go to X, Z, W, V, X. Okay, so that's the idea. Let me try to just check once. Okay, so from X, Y, V, Y, V, what did I write here? Oh, I go back to Y first. I apologize. Okay, let me try to do it again. Okay, X, Y, V, Y, Z, W, then X, Z, W, V, X. Okay, so I pass it through all the edges here. Alright, so that's the idea for Eulerian graph. So remember, all vertices must be of even degree, then you start and end at the same vertex. Okay, then after that, for the second part, we are going to look at how about semi-Eulerian. So which means that you can pass it through all the edges once without repeating any of them, but then you will start and end at different vertices. Okay, so in this case, right, same thing, you have two criteria that you must be able to satisfy. So the first one is that only two vertices can be of odd degree. Then every other vertex must be on even degree. So just now is that all vertex must be even, right? So in this case, is two vertices are odd degree, then the other vertices are in even degree. So where can you start and end? The trail must start at the vertices of odd degree and end at the other vertex of odd degree. So in other words, if you start with a even degree, right, then you would not be able to create a trail. Okay, let me try to give you an example here. So same thing, let's try to check the degree first. So the degree of A, so we have 1, 2, 3. Okay, so this is an odd one. Then after that, degree of B, so you can have 1, 2. So degree of C, that's 1, 2, 3, 4. Degree of D, that's 2. And degree of E, that's 3. Okay, so you can realize here that you have only two vertices in odd degree, which means degree A and also degree E. So B, C, D are all in even degree. So that's why I will know that this is a semi-Eulerian graph, which will give me an open trail. Okay, so remember, when we try to create the trail must start at the vertex of odd degree. Okay, so which means in this case, the odd vertices are vertex A and also E. So we'll start with either one of them. So which means if you start from A, then you should end at E. If you start at E, then you should end at A. Okay, so let's try out the first one first. If let's say I start with A. Okay, so remember that this is where you end, right? So you can have this thing in your mind that you should end at E. So that's why maybe I'll go to B first, then I go to C, I go to E, then I go back to A, then I go to C, go to D, and I go back to E. Okay, so you can see this will give me an open trail. So I start at A, but I end at E. So in this case, you see, why is this thing cannot be Eulerian? Because you can see that if you come back to E, right, then isn't it you can go back to A? But the problem here is if you go back to A, then which means you repeat this edge already. Am I right? So that's the idea. So you will realize that no matter how you draw it, right, you will definitely have one repeated if you were to go back. So that's why it's impossible. So that's why this is just a semi-Eulerian rather than a Eulerian graph. So let me try to write down. So A, B, A, B, C, E, A, C, D, E. Okay, so that's the first one that we can have. Okay, let me try to do another one. Maybe if let's say we want to start with E. Okay, so this is E, right? Okay, so if let's say I try to go to C first, can I do that? Yes, you can. So for example, so I go to C, then I go to B, okay, and I go to A, then I go to D, and I go to E, and I go back to A. So the same thing, you can see that I can actually go back to E, but if I go back to E, then I'll repeat this H. So that's why I cannot draw a closure. So in this case, I start with E just now, E, C, B, A, C, D, E, A. All right, so you can see that I passes through all the edges. So, but then you can see that's like repeated vertex inside here. For example, I actually go through C and C twice. So I actually go through A and E twice as well. But then I do not repeat any edges. All right, and I start and end at the odd edges. Okay, so you see, the odd vertices. So if let's say you want to try out, right, then you can always try out what if you try to start with the, even degree. So okay, if let's say you want to try out with C, okay, so you'll realize that no matter how you draw, right, if I go to E first, I go to D, I go back to C, then I go to B maybe, then I go to A. So you'll realize that no matter you go here or no matter you go here, at the end you can't repeat. You can't finish everything without taking your pen off. So okay, no matter how I draw, right? So now when I'm here, then I'm stuck because I didn't pass it through this edge. Okay, but then if let's say I want to go to this edge, then I need to pass it through another, I need to repeat the edge already. So this is not what we want here. So same thing, no matter where you start, if let's say I start with B, so you realize if I pass through here, pass through here, pass through here, then now I die. Because when I reach here, right, either I can choose to go back to B or I can choose go back to E. But I wouldn't be able to include every edges already. So that's the idea lah. So yeah, you can try out, then you can try to think of like why is that so. Yeah. Okay. Now then let's try to check out the other one here. So same thing, the degree of P. So we have 1, 2, 3, 4. Degree of Q. We have 1, 2, 3, 4, 5. Degree of R. We have 1, 2, 3. Degree of S. We have 1, 2, 3, 4. Okay, so same thing, you can realize that Q and R is having a odd degree. So P and S having an even degree. So that's why first scenario, you satisfy. Okay, then now second case. So remember, you must start with odd vertices. So in this case, maybe let's try to choose to start with R. Okay, so yeah, if let's say you choose to start with R, then which means that you should end at Q. All right, so that's the idea. So yeah, no matter where you want to go through, maybe we go through here first, go through here, go through here, go here, then go around. Okay, so I guess this is quite easy. So in this case, then just now is R, P, then I go back R, Q, S, Q, S, P, Q. Okay, so that's the idea. So let's try again. R, P, Q, R, S, Q, S, and then P, Q. Okay, so yeah, that's the first case. Second one, if you want to try out with R, you can do that as well. So, okay, for example, if you want to start with Q, okay, so you can always, if you want to go outside first also can. So go to P, S, and then come back to Q. Okay, then after that, we can go to R, S, Q, P, R. So you can see that you can't go back to Q because you will repeat these edges already. So this is where you end. So this is supposed to be a semi-Eulerian rather than a closed. Okay, so in this case, then yeah, let me try to write down Q, S, P, Q, R, S, Q, P, R. Okay, so that's our edges. So something you can always try to check with this thing is you try to check out how many edges that you have lah. So okay, for example, in this case, right, you realize that you have 1, 2, 3, 4, 5, 6, 7, 8. So when you try to go through your open trail here, right, you must have a length of walk of 7. So from R to P is like 1. So 2, 3, 4, 5, 6, 7, 8. So do I lack out something? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so that's right. Okay, so same thing when you try to check here. So 1, 2, 3, 4, 5, 6, 7. So this thing must have a length of walk of 7 as well. So from E to C is 1. So 1, 2, 3, 4, 5, 6, 7. So which means your answer is correct. I mean, you didn't left out any edges here. So the same thing for Eulerian as well. So you can always try to check out. So if let's say in this case, the edges that you have 1, 2, 3, 4, 5, 6. Okay, so from A to D is 1. So 1, 2, 3, 4, 5, 6. So that's why you didn't left out any edges. Okay, so I hope that you can get the idea here. So let's try to go through two simple examples before we move on to Hamiltonian. Okay, example 1. For the graph on the right, decide whether it is Eulerian or semi-Eulerian. Define the closed or open path that exists. Okay, so we know that if we want to decide whether it's Eulerian or semi-Eulerian, we need to check from the degree of all the vertices here. Okay, so you can pause the video and try it out by yourself first, so finding out all the degree for all the vertex here. So for A, we have 1, 2. Okay, I'm just going to write like this so that I can go a little bit faster. So 4. So follow the sequence so you do not left out anything. So D is 4 as well. Then E, we have 1, 2. Okay, F, 1, 2, 3, 4. G, 1, 2. H, 1, 2, 3. I, you have 3. And J, you have 2. Okay, so in this case, you will realize that for H and I, you will have odd degree here. So that's why it's like 2 odd degree, then the other one are all even. So that's why this is a semi-Eulerian. Okay, so you can try to write down, some explanation here for your own understanding. Okay, so for example, it has 2 odd vertices. So which means in this case is H and I. Okay, and then every other, so this is very important. You must also mention that every other vertices are even as well. Because if let's say you have more than 2 odd vertices, then which means it is not Eulerian and not semi-Eulerian. Okay, so that's the idea. So if let's say you have a semi-Eulerian, right, then which means that the trail that you are going to form is going to be an open trail. Okay, so because semi-Eulerian meaning that you will start and end at a different point, and the starting and the ending point must be the one with odd degree. So if let's say we start with, let me try to change the color. Okay, so if let's say we try to start with H here. Okay, so you can try to go through. So I'll just write here so that I can, draw a better one. So maybe I will want to go through H, E, B, F, H. Okay, then I settle this part. All right, then after that, I go to J, I, F. Okay, so you can imagine that this might be the last part that I want to pass through because I know that I'm going to come back to I, right? So that's why DCBAD. So I settle this part, DCBAD. So I pass it through everything here already, only left with here, so GI. Okay, then you see I pass it through all the edges here once without repeat anything. Then it start and end at different point. Okay, so now let's move on to example 2. Okay, example 2, police are patrolling inner city streets to prevent crime. So police officers must determine the best route for the officers so that they do not walk along a street more than once. So the officer must start and finish at the police station. Okay, so this is a question where you need to apply what you have learned. So by understanding the context of the question, then you know what to apply here. Okay, so in this case, right, you know that the police are patrolling all the streets here. So the officials also say that they want to determine the best route that the officer do not walk along a street more than once. So if we try to say it in the terminology of graph and networks, meaning that you do not want to repeat the edges, am I right? Because the street is represented by the edges here. So the officer must start and finish at the police station. So which means that the walk that you take must be a close walk as well. So describe a route that the officers can take. So you can try to think of it like this. If you are the police that are going to do the patrolling, right, you must make sure that you passes through every edges. Am I right? So that's the first thing. You must pass through all the edges to make sure that there's no crime. Second thing is you want to find out the best route so that you do not go through the road, you do not go through the same edges again. So you do not repeat any edges. Then after that, the third thing, you want to start and end at the same place. So that's why what is the thing that you want here is basically a Eulerian. Okay, so let's try to check it out. So which means that if let's say you is going to be a Eulerian, then you can try to check through law. So this is 2, 4, 4, 2, and then 1, 2, 3, 4, 5, 6. So this is 6, and then 4, and then 2. So everything here is odd degree vertex. So that's why you are able to actually find out this kind of road. Okay, so let's start with part A. Describe a road that the officer can take. So you will start and end at police station, right? So this is where you start. So let us try to see how to do that. Okay, so if let's say I start with police station, so I'll try to write the station. Oops, station. Okay, then maybe I go to A first. I try to round, the outside part first. So police station, then I go to A, then I go to B, I go to C, I go to D, then I go to E, I go to F. Okay, and I come back to the station. Then after that, I need to continue, right? Okay, because I only passes through the outside. Okay, so now let's try to continue. I go to E, I go to C, I go to A, and come back to E. So E, then go to C, go to A, come back to E. Then now the last one can go back to the station. Okay, so this is the road that the officer can take. So I eventually patrol all the edges here, all the streets here, but then I do not repeat any street and I start and finish at the police station. Okay, so B, explain why is this graph a Eulerian but not a semi-Eulerian? Yeah, because you can see that every vertex here. Okay, so all vertices in this graph are in even degree. Okay, so if you, depends on how many marks the question try to give you, then if let's say you want to explain further, then you can say that all vertices in this graph are in even degree. So this graph has a closure. So that's why it is a Eulerian. Yeah, so if explained further, has a closure, starts and which starts and ends at the same vertex. Okay, try to explain as clear as you can lah. At the same vertex. Okay, therefore Eulerian. Alright, so that's the idea of it. Okay, so now C, if one of the roads connecting the police station with E was closed, would officer still be able to patrol every road? Okay, so in this case then, which means that I think we do not need to repeat the whole thing. So we can try to imagine that one of the road connecting the police station with E was closed. So which means that from E lah, so you can choose any of this is closed. So we can try to imagine if let's say this is closed. Okay, so you can actually check through the thing that we have here as well. So you can see that it's just coincident that just now the route that we try to take, right, we are actually taking the route from E then go back to station. So which means that the officer will still be able to patrol every route, but it's just that you cannot go back to police station anymore lor. So you will go through all of these edges and stop at E. Okay, I hope that you get what I mean. So which means that I go all the way outside, then I go to E first, then after that I go to EC, then I go to E. So in this case, I cannot go back, right? Because if I go back, then I'll repeat this edge. So which means that I do not fulfill the part where it is the best route that you do not repeat the straight. All right, so that's the idea. So C, the answer is yes. Oops, sorry. So because the question asks, would the officer still be able to patrol every route? So yes. Okay, so the other thing that you can try to explain here is you will realize that eventually the police station and the E, right, will become the one that giving you the odd vertices. So this is 1, 2, 3, and then for E, you 1, 2, 3, 4, 5. Okay, so that's the idea. Okay, so you can try to explain it in a detailed way. So removing the H will leave uh let me try, sorry, will leave two vertices, the police station and E in odd degree. Okay, so that's the idea. Then after that, you need to explain it. So because you now have, two odd degree, then after that, the other odd even, right? So that's why this graph will contain an open trail, okay, which the officer able to pass through every edges with the different starting and ending vertices. Alright, so that's the idea. So if you want, then you can always try to note down the road that you find as well. So which means in this case, you can just try to copy down the whole route that you have here. Sorry, it's a bit long. Okay, so the station A, B, C, D, E, F, go to station, and then E, C, A, E. So that's the idea. Okay, so yeah, I hope that you understand how you can apply this idea. Okay, so now let's move on to the next part, which we talk about the Hamiltonian graph. Alright, so this is the last part of the notes which we'll be discussing about Hamiltonian path and also cycle. Okay, so for Eulerian graph just now we said that it must include every edges once. So for Hamiltonian path is a path that includes every vertex once. Okay, so it's actually quite simple like Eulerian, every edges, then for Hamiltonian it's every vertex. So a Hamiltonian path, so which means if let's say you have a path that includes every vertex in the graph once, then the path begins and ends at the same vertex, then it is called as a Hamiltonian cycle. Okay, because a closed path is called as a cycle, right? So which means if you were to explain it in another way around, then which means that a Hamiltonian cycle is a cycle that includes each vertex in the graph once only. Okay, so again, except the first one, because when we talk about a cycle, you must start and end at the same vertex, and that's the part where you repeat the vertex. Okay, so Hamiltonian path or cycle do not need to pass through all the edges. So the thing that you need to fulfill is that it passes through all the vertices only. So you do not need to passes through all the edges. So all the concepts here are very useful for us to solve practical problems. So what is important is you need to understand the context, then you can try to apply them into a situation. So let me try to give you a very simple example. When we have the police, this idea just now, right? If you are trying to changing this map to an idea where you are doing a delivery, so the idea of delivery is to send the food to every of these condominium maybe. Okay, so which means in this case, right, if you are talking about delivery, then do you actually need to go through all the edges? No. So what you need to do is you only need to pass it through all the vertices. Am I right? Because you want to make sure that your delivery reach every of these vertex, but then you doesn't need to pass it through all the edges. But in terms of this police, then which means that you will need to pass through all the edges, which means that you are doing patrolling. So that's why it's important for you to understand what the question want, then only you can apply whether you need to pass it through all the edges or you will need to pass it through all the vertices. Then from there, you determine whether you need Hamiltonian or you need Eulerian. Okay, so that's the idea. So again, always go back to the idea where you understand everything that you are doing rather than memorizing it, because you will have like different kind of situation that you will be encounter, and you will not be able to or say that case one using this, case two using this. Okay, so it will all depends on the situation that's given. Okay, so yeah, something that special about Hamiltonian path and cycle is that you can only identify by using try and error. Okay, so you can try to write down here. Sorry, I do not have the part here. Okay, so you can only use try and error. So which mean that for Eulerian graph, right, if you can recall, just now we say that you can try to check it from the degree of the vertex. So which mean if let's say you have all even vertices, then which mean that is Eulerian. If let's say you have two odd, then the other even, then which mean is semi-Eulerian. If it's neither, then which mean it's not Eulerian, it's not semi-Eulerian lor. But for Hamiltonian, right, there's no such thing, there's no shortcut like this to help you to find that. The only thing that you can do is try and error to see whether you can create a path that includes every vertex once or not. Okay, so yeah, the notes for the Hamiltonian is actually quite short. So let's start with the example. Okay, example 3, list a Hamiltonian path for the graph below. Okay, so in this case, then when you try to look at it, I think it's actually quite obvious. So just make sure that you have a path that you passes through all the vertices and you start and end at different vertices. Okay, so in this case, let us just start with A. So we can go to A, C, H, D, G, F, E, B. Okay, so it's actually quite straightforward. A, C, H, D, G, F, E, B. Okay, so you can see you pass through all the vertices here and you start and end at different vertex. Alright, so that's the idea. So when you try to check, then you can always try to check like 1, 2, 3, 4, 5, 6, 7, 8. So that's why 1, 2, 3, 4, 5, 6, 7, 8, and that's correct. Okay. I know that when you are trying to continue from B to A, then you can are able to get a Hamiltonian cycle. But in this case, the question want a Hamiltonian graph or Hamiltonian path. So that's why we start and end at different point. Okay. Then after that, the same thing for this thing. So you can start at any point that you want, as long as you can pass it through all the vertices without repeating. Okay, if let's say I want to start from H, okay, so maybe I can go to H, G, E, F, I go to B, C, A, then I realize that I cannot because I cannot go through D. Okay, so you see, you can always, this is what is that meant by try and error lah. So for example, when I try to go through this, then I go to B, I go to C, I go to A, then I realize that the last thing I should end at D, right? Because I need to go through all the vertex. But in this case, I'll need to pass through B, then I can only go to D. Then in this case, I repeat my B already, so that's why this route is not correct. Okay, so that's the idea where how you can identify whether the thing that you try to take is correct or not. Alright, so in this case, maybe what I'll try to do is I go H, G, E, F. Oh, sorry. Then I'll try to go through the same thing again. So maybe let us try to go through this part first. Okay, E, A, C, B, D, H, G. Then I realize that I can. Then I start with F. Okay, yeah. So you can always try to like modify. Okay, so the idea is like this. Let me try to go through again what I did just now. So okay, I go through like I start with E just now, but so E A, then after that C B or D H G. Then what do I realize here is I still left out with F, but I realized that I cannot reach F from G because eventually I need to go back to H or I need to repeat my E here. So that's why what I try to do here, then this become the place that I start off, then I try to connect here. So that's why I put a F here. So this is like the route that I can try to take if I want to include every vertex once without repeating any of them. Okay, so again, 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. And you try to check through all the alphabet. Do you have any repeat? No. So that's why it's correct. Okay, so that's the idea. Okay, so now again, you can have all the different kind of answer. Just make sure that you do not repeat any vertex and you start and end at different vertex. That's it. Okay, so let's move on to example 4. So list a Hamiltonian cycle for the graph below. Okay, so the difference is just that you must start and end at the same point here. So same thing, let us try to start with H maybe. Alright, so I'll go to H, D, C, B, A, E, F, G, J, I, D, and then H, I, H. Yeah, I think that's pretty much. Okay, so you can try to check again. H, D, C, B, A, E, F, G, J, I, H. So I pass through all the vertices and I start and end at the same vertices. So in this case, I will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that's right. Alright, so I believe in this case you can start whatever you want. So as long as you repeat, I mean, if you start from A, then which means you will go all the way, then you end at A lor. So if you start from F, if you want to go the other way around, then you can go this way around, then you end at F lor. Okay, so that's the idea. Okay, so now this thing, I guess this might be a little bit tricky. Yeah, so you might want to start with this thing first because you have some overlapping. It's going to be harder compared to this. So if let's say you start with D here, okay, so I can go to D, F, E, G. Then you realize that I'll come back to D. So that's why this is not what I want. Because eventually, if I try to do like this, right, then you repeat the vertex of D already. So this can't work. Okay, so in this case, then I might want to choose to start with the other. So this is why it's called as try and error, because there's nothing that can tell you where to start and where to end. So in this case, maybe I'll try to do, if let's say we try to do like this, to go here, yeah, this work. Okay, so A, B, C, F, E, G, D. So I pass through all the vertex once and I do not repeat any of them. So 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, and then I do not repeat any. So make sure that they are adjacent to each other. So I mean, for example, you do not write something like AF, which you can't reach F directly. Okay, so A, B, C, F, E, G, D. Alright, so that's number 4. Okay, now let's look at number 5. Okay, number 5, a salesman is traveling to 7 country towns to sell flour to the local bakeries. So a map of the town is shown at the right with the vertices representing the towns and the edges here representing the routes connecting the towns. So the salesman want to travel from town A, so this is where you start, to visit every town once on his journey and then return back to town A. Okay, so describe a road that the salesman could take. So in this case, right, when you try to look at it, then you also understand that what is the objective of the salesman is not to pass through all the road. It's actually to pass through all the town. So that's why the thing that you need is actually to pass through all the vertices once. because I mean you do not want to waste your time and energy to actually pass it through the town that you have actually go through, right? Yeah, so that's the idea of it. Okay, so now describe a road. So that's why so in this case, you need to start from A, then you need to return back to A. So that's why it should be a Hamiltonian cycle here. So that's why from A, okay, then you can try to see how you can do that. So let's go to I first, and then H, G, F, E, D, C, B, A. Yeah, that's nice. All right, so yeah, basically I go through here, 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 here. I go through here, here. Oh, sorry, I should go to D first. Yeah, so when you're trying to do that, then you realize that if you go to C first, then later you go to D, then you are stuck there. Because from D, then if you want to go to other vertices, so you already pass it through E and C, so you can't do that. So that's why, yeah. So A, I, H, G, F, E, and then I need to go to D first, and I go to C, and then B, then go back to A. Okay, so this is the route that I have. So you can count A, B, C, D, A, B, C, D, E, F, G, H, I. So that's 9. So plus A, the ending. So that's why I should have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's right. And check whether you repeat or not. Okay, so B, what is this work an example of? So yeah, this is simple. It's a Hamiltonian cycle. Okay, so that's the idea. All right, so if you want to, I mean, this thing, then you can just try to write Hamiltonian cycle lah. If let's say you try to explain further, then you can try to write that because the salesman, okay, must start and start at A and travel to every other town. Every other town once each and go back to A. Okay, so yeah, that's the idea where how do you know that it's a Hamiltonian cycle. Okay, so list the ages that the salesman does not travel on. So you just try to look at the map that you have, then you just try to note down the path. Oh, sorry, the ages. So in this case, it will be the ages AC. Okay, and then sorry, there's no comma there. Ages AC, AC, CE, CG, and then FHF. Alright, so 1, 2, 3, 4. These are the 4 ages that the salesman does not travel on. Alright, so again, try to understand the context, then you'll understand what to do. Okay, so now the last example. So to like a summary of everything that we did for today's lesson. Okay, number 6, classify each of the following graph as Eulerian, semi-Eulerian, Hamiltonian, or semi-Hamiltonian, or neither. Okay, so in this case, yeah, this is like a summary of everything that we have learned today. So let's try to check out the first one first. So Eulerian or semi-Eulerian. So we need to check out all the degree. So degree for A, we have 2, B, we have 2, C, there's 2, D, there's 4, E, there's 2, F, there's 2, and G, there's 2. Okay, so in this case, you can see that it's all even, so which means that you can find out a Eulerian trail from them. Okay, so which means you can start anywhere that you want, so just make sure that you can, what is that called? You can pass it through all the edges and end at start at the same vertex. Okay, so it will give you a closed path. So we can try to write down an alternative. So which means in this case, let's say we try to go through from D. Yeah, I think that's easier. So from D, then go to C, go to A, go to B, go back to D, then go to the other diamond. Okay, so which means we go through like this. Alright, then we pass it through all the edges. Okay, so now the turn for Hamiltonian. So remember, Hamiltonian, you do not have any shortcut. You only can try and error. So if let's say I were to start from A, if let's say I pass it through B, D, then E, F, G, then I realize that at G I'm stuck because I cannot pass it through D again. Am I right? But I still have E that's C that's not connected. So what I can do, I can connect it here. So that's why this will eventually be my path. Okay, but I realized that it's actually an open path because it doesn't start and end at the same point. Then no matter you want to try out, either you start from D first, then you realize that you can't do that as well. Because if let's say you start from D first, right, then what will happen is that you go through D. So if let's say you want to, close at D, right, then you will close here. Then that will be A, B, C that you didn't touch yet. So that's why that's impossible for you to get a Hamiltonian. So which means the more accurate one that you can do is just a semi-Hamiltonian. Okay, so it's a Eulerian graph and it's also a semi-Hamiltonian graph. Then we can try to write down our path as well. Okay, so this is an open path. Oops, sorry, this should be a closed trail. Apologize for that. Okay, so this is open path. Okay, so in this thing just now, CABDEFG. So we pass it through all the vertex ones. Okay, so for this one, so degree for P, we have 3. Degree of Q, we have 3. Degree of R, we have 2. Okay, so in this case, you can see 3, 3, 2. So 2 odd and the other are even. So which means this should be a semi-Eulerian. So for semi-Eulerian, it will give you a open trail. So for open trail, then which means that you should start and end at the odd vertex. Okay, so which means if you start from P, then it will be PQ, PRQ. So PQ, PRQ. So you see that PQ, PRQ. So you start here and then end here. Okay, or the other way, you can try to do QRP, QP as well. So it's just the same thing. Okay, the other thing, Hamiltonian, then try and error again. Are you able to pass it through? I think this one you can because obviously it's just like a triangle that you can take. Okay, then you can go back. So this is a Hamiltonian graph. Oh yeah, I know that you can say that this is a semi-Hamiltonian as well if let's say you didn't go back to P, but remember the idea, so we try to use the most accurate that we can try to do. So if let's say it's a Hamiltonian graph, then we will say that it's a, if let's say you have a Hamiltonian cycle, then we'll say that it's a Hamiltonian graph rather than a semi-Hamiltonian. Okay, so in this case, it's like no matter how you try, it's impossible for you to start and end. So that's why it's semi-Hamiltonian. So for this thing, normally, if let's say you can create a Hamiltonian cycle, then obviously you can create a Hamiltonian path because it's just the matter of whether you want to go back or not. Am I right? So that's why in this case, if you can go back, then we'll say that it's a cycle. Okay, so it's just PRQ, then go back to P lah. Or the other way, RPQ, then go back to R. It's the same thing. Okay, then the last one here. So you can see that the degree of K is 1. The degree of L is 1. Degree of J is also 1. The degree of M here is also 1. Okay, so you realize that 1, 1, 1, 1, so which means that it doesn't satisfy the case where you have 2 odd than the other even. So that's why it's not a Eulerian. Then now let's try to check Hamiltonian. Are you able to go through all the vertices? Are you able to create a path that go through all the vertices? You can't. Because obviously you can see that this is like disconnected graph as well. Because this is like one vertex, this is one edge, this is another edge. You can't reach K from JM. You also can't reach M from JL, from KL. So that's the idea. So in this case, it's neither. Okay, so I hope that this give you a better understanding on everything that we try to learn for today's lesson. So try to spend some time to understand the new terminology, then try to understand what it actually means. Then spend some time to do your homework as well. So if you have any question, then we will be discussing on tomorrow consultation hour. Okay, so that's pretty much for today's lesson. So thanks for watching. So I'll see you in the next session. Thank you.